So now we're ready to solve a problem like this, where we have to draw the internal force diagrams for the frame. Let's take a look at the frame. What's obvious to us is that we have a concentrated moment here of 200 kilonewton meter. We have an evenly distributed force of 40 kilonewton per meter and an evenly distributed force of 20 kilonewton per meter. The system itself is interesting simply because support B here on the right side is higher situated than support A. And so that means that we have to deal with what we talked about before, that we have to set up our two equation with two unknowns. We also have a hinge here at x equals to 2 meter in a global system. But again, let me remind you that this dashed fiber here, the reference fiber, is actually a local coordinate system. So the first thing I should do is give myself like an identity that I probably call this here member 1. And maybe I even call this here 2, like where the force is not acting. And then I have 3, 4, 5, and 6. So I can deal with those. Then the next thing would be to draw my free body diagram. So let's do that real quick. So for my free body diagram, I have to include my forces. And this does not have to be two-dimensional, but it has to be true to the general concept of the frame. So here's my hinge. And now I need to bring in my forces. So you see, drawing a free body diagram for a hinged frame is no different than it is for a beam. And of course I cannot forget my concentrated moment. And now we can define our support reaction. So I'm going to call this here RAY. I'm going to call this RAX. And it's my convention to always put the forces inside to the frame. And sorry, I confused RAX and RAY here. So let me fix that. Sorry, RBX and RBY. And those are global, right? The X and Y, but we have to deal with the other parts now. However, what's important for us to understand is that we can either solve for these two simultaneously or for these two simultaneously. In this case, I would argue that it's easier to solve for RBX and RBY first, because if I make my cut through the hinge, I only have to worry about one force here, whereas if I do it on the other side, I have to include two, but it's neither wrong nor right to do it the other way around. So let us solve the system, and I probably should give myself a little hint here. This was 40 kilonewton per meter. This was 200 kilonewton meter. And then we have 20 kilonewton per meter. So instead of solving it on the bottom, I'm just going to solve it on the right, because then I can see all my dimensions properly. So I'm going to start with RBX and RBY. RBX and RBY. And the way I do that is by setting up two equations with the same unknowns. So first, I'm going to set up the first cut, in which I take the sum of the moments about the hinge. So I set up the sum of the moments about the hinge is equal to 0, counterclockwise positive, and now I can get started. So 0 is equal to, and I need to be true to my directions here. I cannot mess that up. I have to go with what I defined here for now, because I'm going to use these signs like here upwards and here to the left in both equations, and I have to be true to those. So I'm going to start with, let's say, RBX, RBX, and RBX is turning counterclockwise, if I'm not mistaken. Sorry, clockwise. I define it as clockwise about this point, and it's actually acting here. So that gives me a lever arm of 4.5 meters. So RBX times 4.5 meters. And that turns, like I said, counterclockwise. So therefore, sorry, it's clockwise, therefore it's negative. And now I'm going to deal with RBY. And RBY is really acting here upwards. So it has a lever arm of this distance, which happens to be 2.75. So times 2.75 meters. And that is turning counterclockwise this time. So this is positive. And now I need to include my 200 kilonewton meters here. So that turns clockwise, therefore it's negative 200 kilonewton meter. And I have the first equation for my first cut, which is effectively right through the hinge and everything here included. And so what will I do next now? I will actually take the sum of the moments about this point here, pretty much about the support A, and include all of it in my equation. So let's set up the second equation. So I'm going to call that the sum of the moments about A being equal to 0, counterclockwise positive. And now 0 is equal to, and I'll start with my same unknowns, RBX. Now it's important to be careful. So it's acting here and it's turning about this hinge. So effectively it's turning this way around, which makes it counterclockwise. So that makes it positive, but I also have to find that distance from here to here, effectively from here to here in a vertical manner. So that would be a distance of 2 meters. So 2 meters. And now it's turning counterclockwise, as I said, so that's positive. Now I need to deal with RBY. And RBY is really acting upwards, so it's the distance from here to here in a horizontal fashion. So that would be the entire length down here. So that would be 4.75. So times 4.75. But now I have to decide in which direction this is turning, and it's turning counterclockwise, if I'm not mistaken. Yes, so therefore it's positive. And I want to re-emphasize this, right? So here it's plus plus, whereas here is plus minus. That seems strange on the first glimpse, but keep in mind that because you turn about this point in the first cut, and in the second cut you turn about this point, therefore this RBX takes a different rotation, right? It turns clockwise versus counterclockwise on one of them. All right, let's continue because I still have to include my distributed forces here and my concentrated moment. Let's start with the concentrated moment. That is still turning clockwise, therefore it's still negative 200 kilonewton meter. Now let's do the 40 on the top. So 40 kilonewton per meter, and that is acting over a distance of 2 meters, right? From here to here is 2 meters. And then I also turn about this point. So actually I have a lever arm of 1. So times 2 meters multiplied by 1 meter. Now I have to decide, is it clockwise or counterclockwise? And again, this force here is rotating this way around about point A. So therefore it's clockwise, and therefore that is negative. Last but not least, let's do the 20. So the 20 kilonewton per meter multiplied by 3.5 meters. And now it's actually acting directly from here to here. So it's 3.5 over 2 is the lever arm because it's an even distributed force. So that does not make that difficult. So times 3.5 meters, but divided by 2. And now we have two equations with the very same two unknowns, and that will make our life very easy to solve this now. I could have set up the same equations for the other side. In fact, for educational reasons, let's do that right now. Instead of solving these right now, I'm just going to set up the equations for the other side. So let me do that, and maybe I can do it on the same page here. So now I'm going to set up the equation for RAY and RAX. And I'm going to start with the sum of the moments about the hinge is equal to 0, counterclockwise positive. And 0 would be equal to RAX times, I need to be careful, it's the height of that leg of the frame, which is effectively the distance from here to here. So that's 3 plus 2 plus, so 6.5. So times 6.5 meters. And it's turning clockwise, counterclockwise, so therefore it's positive. Next, RAY. And RAY is acting upwards. So it's this distance here, which is 2 meters. So I multiply that by 2 meters. And now I have to wonder if it's clockwise or counterclockwise. And it is pushing up, so it rotates clockwise. Therefore, it is negative. But now be careful, because I have to include my two linear distributed forces here. So the 20 kilonewton and 40 kilonewton per meter. So let's start with the 20 kilonewton per meter, which is acting over a length of 3.5 meters. But now be careful, because the lever arm now is about the hinge. So we're rotating about the hinge. And that means that now I have to pretty much take the distance from here to here, which would be 3 plus 3.5 divided by 2. And that's how I'm going to write it down. So multiplied by 3 plus 3.5 divided by 2. And that also would be in meters. But I'm not done yet. I have to include the 40 kilonewton. So let's do that. Maybe I can get that in the same line here. That is maybe not the best idea. So 40 kilonewton per meter multiplied by 2 meters. That's the distance it's acting over. And in this case, it's easy to see that the lever arm is 1 meter because it's right at the hinge. 1 meter. All I have to do is to decide a rotational sense, which in this case, it is actually going counterclockwise. We're rotating about this point. It's going down on the left of it, so it turns counterclockwise. That makes that positive. But by the way, we forgot the sign for this one here as well. Turns the same way around, so that is actually also counterclockwise. So they are both positive. And now I have that very first equation. Now I can set up my last equation, or my second equation for this cut. So the sum of the moments about B being equal to 0, counterclockwise positive, and 0 is equal to RAX. And what is RAX now? RAX is the distance from here to here. So that would be 2 meters. 2 meters, and it's turning counterclockwise. So therefore it's positive. So plus RAX times 2 meters. RAY has a lever arm of the entire distance from here to here in the horizontal direction. So that would be 4.75. So times 4.75 meters. and that would rotate clockwise, therefore it's negative. And now I have to include all the other ones. So I have my 20 kilonewton per meter times 3.5 meters. And now it's a little bit tricky. That can be really tricky because the centroid here of this force is right in the middle, 3.5, right, to this point. So, but there's only a distance of 2. So let me actually draw that into the system. So the center of that load is acting here. And that would be 3.5 over 2, right? 3.5 over 2. And then technically here we also have 3.5 over 2. And 3.5 over 2 is not 2. As you know, some students sometimes tend to think here at this location. So that is actually, so what we're really looking for is this lever arm. Let me introduce that. So we're really looking at this lever arm from here to here. And there's many ways of how you would define that, but effectively 3.5 divided by 2 is 1.5 plus 0.25, right? So 1.75. So effectively we're looking at 1.75 here, and then here we have 0.25, if I'm not mistaken. So that means that our lever arm is actually 0.25. That is a little bit tricky, so that's why we're solving this problem here, but my lever arm is 0.25 meters. And it's below the support, so the resultant here is actually below this point, which means that we're rotating counterclockwise. So therefore this becomes positive. So this is positive. And now let's deal with the 40. So 40 kilonewton per meter multiplied by 2 meter. That did not change, but what changes is the lever arm, because now our lever arm is acting from the center of this to here, which means I have to account for all this distance here. So that would be 1.75 plus 1 plus 2 halves. So let's actually write it down that way. So 2 halves plus 1.75 plus 1, and that is in meters. And I have to decide for a sign now. So the force is rotating this way around, so counterclockwise, therefore it's positive. Last but not least, my 200, so plus 200, no, negative 200 because it's clockwise, so minus 200 kilonewton meters. And so you see we have two sets of equations that work now. So let me zoom out here and let me highlight for you which ones work. So I have this system of equations here in which we are solving for Rbx and Rby, and I would argue that this was the easier case for this scenario. Or we're going to use these two equations here in which we actually solved for Ray and Rax. And as you can see, those equations are a little bit more complicated, but it's not magical or anything more difficult to solve. Both of those will lead to results. However, we need numerical results for these support reactions to draw our internal forces. I recommend that you start to solve these equations with two unknowns just to get used to it and to be ready for the exam. I will just now provide the numerical values, and I would have found that Rax is actually equal to 64.16, but to the left. That's important. So my result would have been negative, but I don't use negative values in my drawing. So it's just 64.16 to the left, and RAY would have been equal to 2.28, and that is downwards. And so my answer would have still been negative in my two equation with two unknowns. But again, I don't use negative values here or negative values in drawings. So I just make that downwards. I could do the same thing for RBX and RBY, which if I solve them, then I would find 5.84, and that would be positive, which means I assumed correctly to the left. And for RBY, it would be 82.28 upwards. So therefore, my result would also be positive in this equation or in the set of equations. And what that tells me now is that I have solved my support reactions, which I can use to draw my internal forces or internal force diagrams for this hinged frame, which is what we would do next. But this was the support reactions, and I think this concludes the ways of finding one side or the other. By the way, if I would have found only RBX and RBY, then I would have not had to go through all the lengths and solving these equations. I could have just used sum of the forces in X and sum of the forces in Y being equal to 0 to find these other answers. But this way it's a good check to see if I was right and if equilibrium works out. So one way or the other, you always want to check your results, and this is how I can do it here by doing the moment calculations first and then use sum of the force in X and sum of the force in Y for this to balance. And just to clarify on that, so we have RBX and RBY, so let's focus on the X direction first. RBX and RAX and also the 20 kilonewton meter, they all act in the horizontal direction, so they all together have to balance each other, which they do in our case. Similar, RAY, RBY, and the 40 downwards, they all act in the vertical direction, therefore they have to balance each other. And you can see that in our numbers that that is true, and so I can move on to draw my internal force diagrams now. So before I draw my internal force diagrams, it's always helpful for me to bring over my results. So I have RAY with 2.28. I have 64.16. And of course the direction is very important here. So that's 82.28. And I have 5.84. And now I can go ahead and use that information to draw my system or to draw my internal force diagrams. So let's agree that I will start with my normal force diagram here on the side, on the top left, and that is in kilonewton. And so now I have to look at the system and understand what is happening here. So if we remember correctly, there was the only force parallel to member 1 and 2. And let me remind you that this was member 1, member 2, if you will. And then we had 3 and 4 and so on. So I will actually erase those now to draw again, but those are my identities as I said them before. So in member 1, on the vertical left part, the only thing that acts in line of the member, the only thing that's acting here was the vertical force. And see that here we have 2.2 pulling downwards. That means that this entire member must be in tension. I don't even have to make a cut to do that. I mean, a beginner should always make a cut, but I can already see that there must be a normal force that is in tension, and tension is positive. And also it's constant. There's nothing else that pulls on that member. And now remember that we have the reference fiber here, and the reference fiber decides that this is the negative side and on the opposite side is the positive side. So tension is positive. That means I have to have a constant value here. And now you will see for the first time how to draw those diagrams. So you actually do that on a per local basis. So my member 1 and 2 actually look like this. So this is positive, and that would be positive 2.28. And this is the first diagram, or the first part of the diagram, the normal force diagram. The next easier one is the 82 on the right. So let's look at that one. So here again, the reference fiber is on the inside, which means the inside is negative, the outside is positive, and we have 82.28 clearly pushing on this member here. That means it's pushing up. So that means this is in compression, and compression is negative. So that means I have to at least start out here on the left side. But if we remember, there was no other force acting anywhere here on this. Well, there's force acting here on the top, but there's nothing really going on here, and certainly nothing parallel to the axis of the beam. So therefore, I might as well draw a negative box there. And this becomes sometimes tricky for somebody who has never done this before. And I'm going to exaggerate that corner up there. So, because I want you to understand that the part for the vertical member has not anything to do with the horizontal member. Of course, they are connected to each other and the values are dependent on each other. But in terms of this corner here, that is like not related of what you draw for this part. So students often try to make sense out of this member and this member and this member together, but no, this is independent of this one for the sake of this diagram. So in fact, let's start to look at this. So now we need forces that push this to the side, or like that actually push along the axis of this member. And I guess the easier one to start with is using the force down here. If I were to make a cut here at the system up here, you can include all this and bring your internal forces here. But what you would find is that your normal force is only affected by the 5.84. And so that doesn't change anywhere to here, and it also doesn't change anywhere here, because remember, you only had a distributed force up here and nothing else. So the normal force diagram is almost done now. It's very easy to draw. And again, I'm going to exaggerate this. So I'm going to draw it up to here. And then I have to go back to 0 at the corner. So I'm going to go back to 0 there and back to 0 there. And this now is also negative because it's in compression, right? The 5.84 is pushing on that. And the 5.84 is minus 5.84. I also forgot to make this here negative 82.28. And now I'm effectively done with my normal force diagram. Of course, I will explain to you a few things real quick. So I say again that this 5.84 here has to close and go back to 0 at that corner, whereas the 82.28 here, of course, has to go also back to 0. So all this has to be closed. And you can always convince yourself by cutting here and calculating the normal forces. You can convince yourself cutting here and calculating the normal forces and so on. So what students often do is they want to somehow connect this point, like the horizontal to the vertical member. Please don't do that. Look at them individually, if you will. Or if you're in doubt, make a cut. Same thing here. They are independent of each other, if you will. Of course, we will see something related now when we talk about the shear force diagram, but for now, that is what we're looking at. One last word is students wonder, okay, here the 5.84 makes sense in context of this, but what about here? There's 64.16 here, and that is also horizontal. So how does that balance this? Yes, that is true, but don't forget that there was an evenly distributed force here. In fact, I'm going to draw that in here for you real quick. So there was an evenly distributed force here, I believe, of 20 kilonewton per meter. And so that cannot be forgotten, and that actually brings the 64, and this force actually back to a compression of 5.84. So that's what's going on here. It was just easier in my case to start here from the right side. And I believe that concludes our normal diagram. So now we can move on to the shear force diagram. Let's do that. And let me just use the color blue in kilonewton for the shear force. And now we have to start again. So I guess it's helpful to once again bring in my arrows. 64.16 and 2.28 and 82.28 and 5.84. And now I wish I could rotate this picture by 90 degrees, but it's virtual, so that doesn't really work. But I want you to imagine to actually look at this as being on the bottom, right? So remember what we've done in the past when we had like horizontal members. We always said, hey, if the reference fiber is on the bottom, we can start on the left side and then follow our arrows. So that works here as well, because effectively this arrow is under the reference fiber, and so I can just follow that arrow. And remember, there's the evenly distributed force here, so I'm going up, and then I'm going down, 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 and then nothing happens, nothing happens, nothing happens, and it goes back to 0. And the same is true here actually on the other side, except that now I'm on the right side. And so if the reference fiber is on the bottom, then this force here is on the right side of this cut. So if I look from the left to the right on this now, then of course I have to invert my logic. So I'm actually have to go against the arrows, but I will get there in a second. However, here it's true again, right? So I can start on the left side, and I can start with 2.28 down, because that's the only thing that's happening here. And then there's a distributed force here, which I probably should include as well. So let me remind you that there is actually 40 kilonewton per meter acting in this direction. And so we also have to think about that. But let's take it one by one. So first, I have to actually go up by plus 64.16. And then I have to, let's pretend that this is 1.5 meters above. So I'm going to pretend that this here is the line where the evenly distributed force ends. And so I have to go down from 64.16 over that distance with actually 20 kilonewton per meter. And so I will pass through 0 actually, and that will become interesting when we talk about the moment diagram. Let me just draw that properly for you. So here we go. And then I have the case where nothing happens, right? So nothing happens, nothing happens, nothing happens, nothing happens. And now similar to the normal diagram, it has to go back to 0 again. And again, I want to point this out to you that this part here actually belongs there, but I find it easier to communicate to students that it has to go back to 0 if I don't draw it on top of this black line. So that goes back to 0 there, and I have negative values here, positive values here. And what is my value down here really? It's effectively 64.16 minus 20 times that distance, which also happens to be negative 5.84. So this is negative 5.84. And that diagram was easy to draw. And again, I'm drawing this right now because I already did the cuts and so on. So if you're in doubt about this, feel free to make the cuts. It will always help you. But the reason I was able to draw this is because I just flipped this 90 degrees on its side and then I followed my arrows. I went down, 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 down. nothing happens, and then it has to go back to 0. So, and now it becomes interesting because we have to do the very same thing for the other direction. And I guess it's easier if I zoom in here. So I have to first go down now. So I'm going to focus on this horizontal member here, the entirety. Remember, there's an evenly distributed force here. So I am going to first follow my arrow, which is the support reaction on the bottom, which was negative 2.28, or it will be negative 2.28. So let me draw that. So this here would be negative 2.28. And then I go down by 40 for every meter, right? So I go down, 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 down until I hit the hinge, because that's where the evenly distributed force ends. And if I go down with 40 over that distance, I end up as minus 87.28. Sorry, minus 82.28, right? Not 7. 82.28. And then again, nothing happens. Nothing happens. And then it has to jump back up. And I will explain that to you in just a second. So this jump here originates from this force, right? So this brings it back to 0. And so now I'm done with that part. All of this stuff here is negative, of course. So all this is negative. And now, last but not least, I have the part on the right side, the vertical part. And I make my life easy. Instead of starting from here, which I could do if I move my head or like my paper and rotate it by 90 degrees, then I can just, I could follow my arrows if I start on the left side, but I want to start on the right side. So I just go against my regular logic. So 5.84, the arrow goes down. So that means I have to go up on my diagram. So 5.84, that would be positive if I'm not mistaken. And then nothing happens again, right? So nothing happens. And then I have my diagram here, and this is all positive, and it is positive 5.84. And you see, I already drew my shear force diagram without running any numbers. Don't get me wrong, you can run numbers, and you probably should, but ultimately you should reach the point where you can use that logic to move your way around. So I want to emphasize, yes, here there's a hinge, and often, as I said before, when we talked about hinge beams, students want to think of the hinge as being 0, but that's only true for the moment, and we'll come to that when we talk about this diagram down here. But for now, there's a value here. In fact, it's the value 82.24, and then it starts sloping up. Last thing for me to do is to calculate pretty much this distance here, because remember that where the shear force goes through 0, my moment is maximum, and of course I want to calculate that. So I want to really understand this distance here. So let me zoom in there. And I have these distances. And you can find that in many ways, similar triangle or something like that. So x actually happens to be 3.208 meters. And so that leaves this here with 0.292 meters. And this is different for how, like, the point of this lecture is not to show you how to calculate that. We talked about that in previous lectures, but it's either similar triangle, or you can set up the equation for this sloped line here and then set that equal to 0. All right. Now, last but not least, we have to focus on our moment, and let's, as always, do the obvious parts first. Moment in kilonewton meter, and we know that it must be 0 there. We know it must be 0 there. We know it must be 0 there. We also know that I have a parabolic function here, x squared. I also have x squared there. And then I have it linear. So that would be x and x, but don't be fooled. Remember that there was a concentrated moment somewhere here. So there I must have a jump. And then last but not least, here I must have a function of x. And by the way, here also I have x. But I will erase this now just to not confuse myself when I go through those drawings. But I know where it's linear and where it's not linear and where it's parabolic and so on and so forth. So it always helps to look at the shear force diagram at the same time. And let's start at the bottom part. So here we know we have a positive slope, negative slope. So that means that my parabolic function must go like this. So again, I started at 0. So it must go up, and then go down at some point. So, and here where I have the maximum, that distance would be 3.208 meters. We'll come back to that in a second. What's next easy thing to know? So I know that it's 0 down here, and it must be linear on this one. And in fact, it must have a slope of positive 5.84. So therefore, I might as well draw a linear line. And that looks like this. And I'm going to zoom in to complete this. And what is the ultimate value at the corner? The value at the corner is effectively the support reaction, which is 5.84 multiplied by the length, which that length is 3.5, if I'm not mistaken. Or is it 4.5? It's 4.5. So 4.5 meters. Right? And so the value at that corner is actually negative, by the way. And so that is negative 26.29. All right, and we know that this is negative. And remember that at the corner it's constant, so I'm going to use a different color now just to emphasize this better. But this line here is actually also the very same value. And so now I have to be careful, because my first attempt or my first intention would be, hey, it has to go to 0, so it's easy to draw this. But that means you forgot about the concentrated moment. So let's erase that. So I have to actually go up first, and I have to go up with a slope of what I can read from my shear force diagram, 82.28. So that means that ultimately I will have to go, because it's 1 meter, right? I have to go up in that direction. Then there's the jump of my concentrated moment, and then it has to go to 0. There's no way around that. So this is a must. I used to jokingly say that if a student puts a value here in the moment diagram, that I have the right to fail the exam, but obviously I only subtract points. But please understand that if you do not put your moment diagram through 0 here, you did not understand the hinge, and you need to pay more attention to the details that we're trying to discuss in these lectures, right? So this is negative, this is positive, and then I guess I have to zoom in here. This is negative. All right. I can also calculate now the value at this corner. Well, so I have to calculate the value at this corner here. And of course, my slope cannot change at the hinge. So effectively, I have something that goes like this. And pay attention to your shear force diagram. Let me point you to it. So your shear force diagram does not go through 0 here. That means that I cannot reach a maximum here. Well, I mean, there will be a maximum relative to this, but there will be no change in slope, right? So I will have the maximum value right at the corner. So let's draw that. So it will look like this. And it will close here. And this is positive. And again, it's a 90-degree corner. Actually, it doesn't matter if it's 90 degree or not in this case when it's the moment, but of course the value here on both sides. So M1 and M2 are equal to each other. And again, linear. I have to make a linear connection between those points. So let's do that. Technically, my drawing doesn't show it, but technically this tangent here actually is tangent to the curve at that point. But the last thing for us to do is calculate the maximum moment and the value here, because it's also the value here. And I guess we also need to calculate those values, which I believe we already did effectively, like I said. So from here, the slope up, so minus 26.28 plus that slope here. So let's get started on that. So we have a value of plus 55.99. And then we have negative 144. And in the corner, we have 84.58, and that's positive. So here we have plus 84.58. And then last but not least, our maximum value here. And I just recommend that you go ahead and make a cut here and go through that exercise of calculating that. In fact, I'm going to do that real quick for you. So I'm going to calculate. I pretend I cut the system at that location. And I put my distributed force on there. And of course, I have support reactions, which are actually 64.16 and 2.28, although I don't need that 2.28, but I need you to understand that I just cut the system here, and I'm now calculating my moment there, and this distance here is 3.208 meters. So now I can calculate my moment. By sum of the moments is equal to 0, and 0 is equal to minus m, no, it's plus m, max plus 20 kilonewton per meter multiplied by 3.208 meters, and now multiplied by 3.208 divided by 2 meters. And of course I need to account for my support reaction, but that one is acting clockwise, so therefore it's negative. So minus 64.16 kilonewton multiplied by 3.208 meters. And if I solve all this, I actually will find the maximum moment, and the maximum moment actually happens to be positive 64.16, if I'm not mistaken. Sorry, that's not true, 102. So 102 is, so therefore M max is equal to 102 kilonewton meter. So what we now know is that this value here is 102. So 102 kilonewton meter. And that is an important value because that's the maximum value. You can now do the same thing at this location, and I recommend you do that because in an exam you also would have to provide that value over there. And in the same way, by the way, you can also calculate the value at the corner or everywhere, anywhere you want really. So it's always in the cut. But let's review this real quick. So now we have drawn for the first time the internal force diagrams for a rectangular frame, normal force, shear force, and moment. And as normal before, or sorry, that's a bad choice of words here, but as we did before, we used our same logic. So for example, for the normal force, tension and compression is important, and it defines our positive and negative values. If nothing changes, then it's just constant, and that's mostly the case for us in this class. And we were able to follow that logic here. For the shear force, same thing as before, except you have to get comfortable with the fact of like rotating your system by 90 degrees to follow your arrows. So here 64 up, down, 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 nothing happens, nothing happens, nothing happens, boom, back. And then the same here, except at this corner you have to kind of look down here and use that 2.28 because along this beam there's nothing else that's acting vertically. So only that goes down, and then it goes down by 40 per meter. Then nothing happens, and it goes back up. And last but not least, here on the right side, because the reference fiber is on the bottom, I just followed that logic and I inverted it, right? So instead of going, I started on the right side, and instead of following my arrow, I went against it. So I went 5.84 up, and then nothing happens, and then it has to go back to 0. And let's compare this, right? So the 5.84 here is reflected in the horizontal member for the normal force. 82.28 in the right member is reflected in the shear force for the horizontal member. So you see whatever is vertical here carries over to the shear force in the top member. And the same is true here. 5.84 at this corner for the vertical member is reflected here in the horizontal member. 2.28 is reflected right here. And so that's a way you can check your logic there. Similarly, the moment diagram down here relates to the shear force diagram, just like we learned before, where the shear force is the derivative of the moment or vice versa. Just be careful when you follow your integration logic, right? Because also you could say that your moment is the integrated shear force. Be very careful when you go down that route because you want to not forget about the integration constant here, which is the concentrated moment at that location. So with that said, I think we now understand how to calculate frames that have right corners and that have a hinge, right? So the hinge was the starting point that challenged us because we now had to understand that we can solve the support reactions in a very specific way. But then after we found the support reaction, nothing new, nothing different than before. We just had to follow the logic and of course adapt it towards our sloped views, if you will. So that concludes this problem, and I believe we have solved for all the significant values and we have deciphered each part of the frame.